He explained this phenomena in terms of total internal reflection of sound waves. So total internal reflection already starts introducing as an important concept of this type of modes, that these modes have very little leaks, so very little losses. So this is an example of acoustic whispery gallery modes, and here we have examples of optical whispery gallery modes, and these are the things that I'm more interested on at the moment. So this is, for example, like now the role of the person who whispers will be played by these lasers that enters the cavity and start rotating around the cavity. And this is the cavity now, for example, can be a micro droplet of water, for example. It can be a sphere of fused silica. And this is an example of most modern realization of microresonator, whispery gallery modes microresonator done, for example, with microtoroidals. As you can see, the scale of this object it's very small. So the question, of course, is why are we interested in this specific type of microresonators? Well, it turns out that the power, intensity power circulating inside the cavity is proportional to the quality factor of the cavity and inversely proportional to the mode volume of light. So the quality factor, it tells us basically how good our cavity is. If we put a photon inside our cavity and this photon lives for a long time, that means that our cavity is very good and our quality factor is going to be very high. With droplets, for example, with water droplets, their quality factor is around 10,000 to 100,000. With the silica microsphere, done maybe 30 years ago, the quality factor was around 1 million. And with this type of structure, the quality factor is higher than 100 billions. So for sure, whispery gallery modes are naturally a mode with a high quality factor, but although the technical, like there has been a lot of improvement in how people are able to generate this type of structure in order to extend as much as possible the value of the quality factor. If you look at this picture, you can see that the light, when travels inside this sphere, it doesn't spread around, but it's a constraint on an almost one-dimensional curve. That means that the mode volume of this light mode is also very small. Combined together makes the circulation of light inside this structure really high. And what do we do with very high intensity circulating inside our cavity? Well, we can unveil all the nonlinear interaction that light can have with matter. In other words, if we consider the polarization of the material, normally we stop here. We consider only the term that is proportional, is linearly proportional to the electric field, but now we need to consider all the nonlinear correction of polarization. I would like to stress that in general, this term is 0. The second order susceptibility is 0 for isotropic media. But in this talk, I will consider material where this term chi2 is not 0. And this is true for material like, for example, lithium niobate, which are not centrosymmetric. This is a very, very beautiful picture, a very beautiful sketch of what a frequency comb is, because ultimately, I have not said why are we interested in a whispery gallery modes resonator. So as explained yesterday by Sergei, whispery gallery modes are very interesting from the optical community because they're able to generate a frequency comb. Here is a sketch. We have an input, a monochromatic waves that enters our microresonators and interact non-linearly with the cavity. We generate, for example, a pulse, and then this pulse leaves the cavity. Let's imagine that this process, we repeat this process, and this process becomes perfectly periodic in time, right? That means that we're going to have an input power with a single frequency line and an output power with many frequency lines, and all these frequency lines are going to be perfectly equispaced, where the spacing is going to be given by 2 pi over t. So simple frequency, simple Fourier analysis. But what I want to stress is the fact that mathematically, a frequency comb will be nothing else than a stationary solution for an equation that governs light that travels inside this cavity. And this equation will have to take into consideration the fact that lights keep coming inside and outside the microresonator. Well, yesterday, for example, has been mentioned the Luggiato-Lefebvre equation, which is the master equation to describe a frequency comb if Chi2 material if the second order susceptibility is not present. Right, so this is a much better picture of a frequency comb. And again, we can see that the frequency comb is now used for many applications. Why? Because the frequency comb is nothing else than an optical ruler. So it represents the state of the art of time and frequency measurements. And so where does our contribution come in? Well, a frequency comb is an optical ruler. So to be a very good optical ruler, in general, overruler, you need to be precise, and that's what a frequency comb is. But also, ideally, you want to be able to cover as much part of the electromagnetic spectrum as possible. So one should say, okay, well, let's generate a soliton which is very sharp. That means that we're going to have a frequency spectrum that is very broad. But that goes against the whole idea of this frequency comb generated in this system. Because we have an input, our input laser have very low power. This object is very small, and we want to try to have an output power that covers the maximum extent of the electromagnetic spectrum. Because of that, we decided to consider a microresonator that is made with quadratic nonlinearity, and to make use of what is known as called the second harmonic generation. Second harmonic generation is also one of the earliest nonlinear effects in optics. I send a red beam inside a dielectric, and my output is going to have a red beam and a green beam, for example. So this is the sketch, again, of what we were expecting to study. A frequency comb around the input laser, and a frequency comb around twice the input laser frequency. Okay? I would like to also point out that these two spectra are very well separated. That means that in physical space, I can describe this with my function psi p, and this other field will be described in physical space by a function psi s. So these are my equations. We're going to have one equation that describes the dynamics for the first harmonics, and an equation that describes the dynamic for the second harmonics. These equations are coupled through nonlinearities that allows energy to travel from the second harmonics back to the first harmonic. We're going to have dissipation. Forcing will be only in the first harmonic equation, because I want to pump in the first harmonic and generate the second harmonics. This is the dispersion material in the bracket. So these equations have a lot of parameters, a lot of free parameters, but I would like to point out that the most important one that I would like to stress the importance of these two deltas, which are the laser detunings for first and second harmonics, and the difference between the group velocity for first harmonic and the group velocity for second harmonics. In hydrodynamic terms, it basically means that these two fields, they travel with a relative velocity with each other. And I will call this term Walkoff. Okay? So the first problem that we had to deal with when you want to model this system is how to model the dispersion relation for our material. So this is a finite size system. That means that I'm going to have to deal with a discrete set of eigenfrequency. So how do I find them? Well, this is the easiest way that I can think of to identify Whispering gallery mode eigenfrequencies. We just assume the easiest dispersion relation for light, and we say, well, that the wavelength on light is just a multiple of the resonator length. Then we do simple algebra, and we have a formula for our Whispering gallery mode eigenfrequency. Well, this is obviously really a brutal approximation. The refractive index, for example, is constant, and so we want to go to a better approximation. And so here there is a reference to a paper with a semi-analytical way to evaluate the eigenfrequency mode. And then what you can actually do is to solve really Maxwell equation inside a sphere and find the eigenfrequency that corresponds to a Whispering gallery mode. note that the whispery gallery modes, it is a mode where this mu basically is going to be really high. And this is student Dimitri Danila became extremely proficient in solving and using these techniques, and we were able to find our dispersion, the dispersion relation for our material. So obviously, if we want to study the second harmonic generation, everyone has to first satisfy energy and momentum conservation that in optics can be translated as a phase and frequency matching. Okay? So here I want to, now I can present what my delta P, my laser detuning is for first harmonic and second harmonics. So here is my set of discrete eigenfrequency for my cavity. This is the angular frequency of my input laser. And this is the closest eigenfrequency to this input laser. So the distance between the two is the laser detuning. And this is actually what the experimentalists use to scan the cavity. And similarly, I will have the same thing for second harmonics. So omega s, I denote omega s as the closest eigenfrequency to 2 capital omega. So if we do the simple algebra, what we see is that the delta s can now be rewritten as 2 delta p minus a term epsilon, which I call epsilon because it's in general small, and I call it, this is basically a frequency mismatch. So really, this is a feature of the fact that we're dealing with a system which is discrete, a discrete set of eigenfrequencies. So these, in other words, these are going to be quasi-resonance. And I want to stress the importance of this epsilon because different epsilon will make a completely different physics. So let me rewrite the equation in a more simple way. For example, I do a Galilean transformation where I place myself in a frame of reference, then move with the group velocity of the first harmonic. So the first derivative goes away in this equation, appears in the second equation, and now denote u as the difference between group velocity first of second harmonic and first harmonic. And now as well here you see this epsilon is explicitly present. So we want to find soliton solution, as mentioned yesterday by Sergei, soliton solution on Lujato-Lefebvre equations, or in general in cavities, they live on the top of a constant background. So the first thing that you need to do is to find this constant background. To find the constant background, we need to solve a homogeneous solution associated to our previous equation. That means let's remove all derivatives. We end up with these two equations that if we consider epsilon negligible, what we get is two tilted resonance. Red is for first harmonic and green is for second harmonics. Here this plot is done in terms of detuning for first harmonic, but everything is dimensionless in this plot. So let's now consider the case of epsilon to be not negligible at all and even much larger than dissipation. Well, in this case, we can write the second harmonic fields to be equal to psi square of the first harmonic. We can substitute these into this equation, and we get an equation that now shows the typical cubic nonlinearity present in the Lujato-Lefebvre equation and in NLS equations. Right? And this is not surprising because this is the well-known cascading case where a chi2 material behaves effectively as a chi3 material. And as you can see, in this case, one of the resonance disappears and we have a single resonance for first and one for second harmonics. There is still something here because I wanted to emphasize the fact that they don't disappear abruptly, but they shrink away. So this is a very similar resonance that one can see as well in the Lujato-Lefebvre equation. So finding a background on which the soliton lives, it's the first step. Then we need to check if this background is stable, because if it's MI stable, then we're not going to find solitons. And then the second thing that we want to do is to check the presence of a gap in the weakly dispersion relation. What does that mean? If we have a solitary wave that moves with velocity v, these solitary waves can exist only if no small wave amplitude exists that have a phase speed that is exactly equal to v. What do I mean? Let me be a bit more clear. So I consider my homogeneous solution and I put on the top some low amplitude oscillation, right? This is my ansatz, I put it in my equations, and I linearize my equation, and I solve an eigenvalue problem for omega, and I plot my weakly dispersion relation. Actually, here I'm plotting the phase speed of my waves. And you can see that there is a gap open. That means that I fix all the value in all the parameters in my equation, and there is a set of velocity in which no small amplitude waves can propagate. That means that this is a possible velocity for our soliton. So I found my homogeneous solution. I check if the gap is open. That means that this is where my soliton can exist. I want to present this because when walk-off is not present, I have a gap open. And when I add walk-off, my gap shrinks. And eventually, there's going to be a critical value of walk-off where the gap is closed and soliton will stop, will chase existing. Another important feature that all I presented in this calculation was Hamiltonian. Otherwise, this weakly dispersion will be imaginary. So let's reintroduce dissipation. Now the system is not Hamiltonian anymore. That means that the total momentum of our system here, right? The total momentum is going to be a combination. It's going to be the sum of MP plus MS. I write the time derivative, and in general, it's not zero. Although there might be a combination of these two terms in such a way that this is going to be zero. That means that it is possible to find stationary solution for a dissipative system. The momentum will be in general dependent on the velocity v. That means that the value of the dissipation is going to select a specific value at which the soliton can travel. And this is, again, nothing strange. It happens as well, for example, when we consider Raman. So we now have all the ingredients to find soliton solutions. Okay, and here I plot. So, for example, in this case, like, okay, this this background is a good candidate to find soliton solution, and I do find solitons, and I can extend I can check where they exist, varying the tuning, but also varying the input laser power. So here is omega is the power, and the relation between omega with W and the H, so the forcing that present in my equation is written here. But what I can see is that all the solitons, when no walk-off is present, that means no relative velocity between the two fields, all the solitons are stable. Their range of existence extend until the B-stability point. This is basically this blue point extended for different value of H. So this is already surprising, and probably for an experimentalist will be even an experimentalist will be happy because it means, okay, I'm going to find very stable solid frequency comb if I don't consider walk-off. But what happens when I do include walk-off? Then not only the region in which soliton exists shrinks, but also there is a region in which solitons becomes unstable. So what I can do, I can now consider a point on this unstable region and run numerical simulation starting with an initial condition of my solitons that is going to be, I place myself in a frame of reference that moves with my soliton. That means this guy doesn't move. This is in time, in round trips. Then an instability starts developing, and then we have the formation of a breathing structure. This structure is very stable, and I extended the simulation even further. And if I take a window of time and I do an FFT in time and space, I can see the presence of a coherent structure, as you can see here, this perfectly obliquous line. And here I plot as well this dashed white line that represent the weakly dispersive relation that I show here. But now I show that in the frame of reference that moves with the velocity of the soliton. The soliton is stable here. So if I do a radio frequency spectrum, that means doing an FFT of the total input power, what I see is that apart from the zero background, I see a peak at 0.01 gigahertz that actually represent the oscillation of our breather. So once I want to show you as well this picture, because when I don't know if you can see it, but from the talk of Pierre Suret, he showed that a soliton gas it appears, basically there is no distinction between a soliton gas and an MI gas. And so when I looked at this picture, I can see this is the same case I showed you before, but for higher input laser power. So the instability, it gets stronger. The soliton is stable. It transits into a breather. And then this breather starts bifurcating into many more breathers and eventually becomes a more chaotic state. And I call this a breather gas. I mean, I don't know whether it's correct to call it breather gas. This is the same plot, the same Fourier transform in space and time for a windows taken after this simulation becomes stationary stable. And as you can see, there is no more any presence of coherent structure in here, and as well is not any presence as well in the radio frequency spectrum. So I wanted to check, but what is then a soliton gas, for example, in this system? Well, it's not easy to show that, is to see that, because to trigger instability, I need walk-off. And if I don't consider walk-off, then all my solitons are stables, right? So what I've done, I thought, okay, well, let's remove walk-off. Let's remove walk-off, and let's sit on the top of this other homogeneous solution, which is unstable. So the system is going to fall somewhere. It's going to eventually, sometimes it falls into a soliton solution, sometimes it falls into something else. And for example, in this case, for the same parameter of the simulation I showed you before, I see a slightly different configuration. And I thought, is this a soliton gas with respect to the breather gas that I showed before? Well, to distinguish then, what I've done is I plot the PDF of the power intensity. This is for the soliton gas, and this is for the breather gas. And you can see that there is a clear distinction between the two. There is a peak for the soliton gas on the background because the soliton lives on the top of the background. Then there is another peak here. This is for second harmonics, and blue is for first harmonic. It's the peak where the amplitude of the soliton. And if I consider walk-off, then I induce instability in my solitons. They become breathers. And what I can see is that the PDF is way different. And especially, it plateaus from 0.2 to 0.8, which is actually the typical amplitude of the oscillation of my breathers. So this is all. Thanks for the attention.
Thank you. Any question?
Thank you. In your breather, first and second harmonics, are they still sort of together?
Yes.
They're breathing but not
Absolutely.
separating?
Absolutely.
Okay.
Absolutely.
But did you observe separation of first and second harmonic in some regimes?
No. That's actually an extremely, that's a very good remark, because that's also something that at the beginning I was thinking, okay, if they locked while they are in a breathing, while there is this breather state, what happens when they transit into the chaos? Are they still locked? And they actually are. They actually are locked. And I hope I put a picture. No, I didn't. Very bad. So what you can check, since the system reaches it becomes stationarily stable, the momentum, again, it won't be zero, but it would be statistically zero. But what you can measure is the ensemble average of the momentum for first harmonic and the ensemble average for the momentum of the second harmonics, and you still recover this ratio that is determined by dissipation. And we call that turbulence locking, because we were not expecting the fact that despite reaching a chaotic state, first and second harmonics, they still move locked together.
Thanks for the talk. Did you compute anything about the stability of your solitons and the transition to the breathers? What kind of a bifurcation is associated with this?
Well, yeah, this is a standard Hopf instability. So yeah, that's.
In optics, is there any toroidal structure having chi2 being dominant? Does it exist physically?
Uh,
Because I am aware of a silica toroidal structure in which you have chi3, but does it exist with chi2 being dominant?
Yeah, I mean, if I understood correctly, your questions like this, all these results have been as well. So the realization of a secondary harmonics comb, we did publish it in collaboration with a Freiburg group where they did use a whispering gallery mode made of lithium niobate. So yeah, also like to mention, I forgot that you can see these two equations that I plot. You can find a better description of what I gave into this reference here, where they are derived from Maxwell equation, but also you can find a previous derivation of very similar equation by Stephane 30 years ago, but for a ring cavity, for a fiber ring, I guess.
Any other question? So if no, let's thank the speaker again and move to the next one.
Thank you. So I can leave this. This is yours, right? Okay, thank you very much. No. Yeah.
Okay, next speaker is Marin Mossman,
Oh, thank you for pronouncing it right.
and she will talk about probing matter wave with a dilute BEC.